Hello everybody, my name is David Christiansen and I'm here from IT University of Copenhagen, but I've got a 4-month internship with Galois down the road, so but this is all sort of part of my PhD project rather than stuff I'm doing with Galois. So the title here is very long and impressive, I think. At least it intends to be. It's Type-Directed Elaboration of Quasiquotations. And the subtitle is perhaps a little bit more informative, and it's saying, high-level syntax for low-level reflection. So what this is all about is adapting the high technology of the Lisp of the 70s and 80s to the modern world of functional programming with dependent types. More on that in a minute. So the issue here is that dependently typed programming can sometimes require that you're writing very large proof terms. And this isn't very fun. There's some kind of fundamental thing going on, but I don't know exactly what it is. But they're both sort of compile time metaprogramming. It's probably closer related to something like template Haskell, where you have something that gets type checked afterward. These are all sort of so yes, they're all instances of compile time metaprogramming, but the specifics are different. Yeah.
So the advantage of, or one advantage of tactical languages is they don't have to terminate, right? They can be very complete.
Yeah.
So does that, I assume that's a limitation here. I mean, it's compile time only, so if your compiler doesn't terminate, I guess that's okay. But is that something that you have to worry about, like that your tactical language isn't as powerful?
You just tell the compiler not to terminate, not to run the termination checker on this chunk of code, and then you're in the equivalent situation where you can cross your fingers and wait until you get bored and then stop it.
Okay.
Yeah.
Is it a single phase, or is there potentially multiple phases depending on what's been transformed?
So the way things work in Idris is there's one phase where all of this is happening, which is called the elaboration phase. I'll get into that in a little bit. In principle, you could also do it with more statements. I'm not sure why you'd want to for this kind of direct system, but there's probably a good reason. So just because I don't understand something doesn't mean it's without value. Okay. So it's a compile time only thing. The results need to pass the type checker. That's the key, is that we're doing all sorts of ugly stuff ahead of time because we have this type checker at the end that can say what you did is okay or what you did is not okay. Do it again. And this is useful for proof automation, but it's also useful for a couple other things in Idris. We have something called error reflection, which is where error messages can also be reflected to a data type and then rewritten. So if you have a domain-specific language, you can rewrite the errors to be domain-specific errors and show them in this sort of custom notation that you have. There's also potential to use it for code generation, but people haven't really explored that very much. But the template Haskell people do that quite a lot, so I'm sure there's a lot to be done there. So, inside of Idris, we kind of got a compilation process that looks like this. First, there's some sort of fairly trivial desugarings done, which are purely syntactic rewritings. So you replace do notation with bind operators, and you replace idiom brackets with applicative operators, and these kind of things. Once you've got this desugared Idris, then there's a process called elaboration, which constructs a program in a sort of a core type theory, which is called TT, which I believe originally was short for type theory, and then somebody noticed it looked like a big pie, and we thought that was fun, so now that's the official excuse. And then after that, there's various transformations to different compile backends. So you can spit out JavaScript or C or LLVM bytecode or a few other things. The part that we're going to be looking at today is all here in the elaboration phase. The reflection data type is not the most pleasant thing in the world to look at. Here is the definition of almost the entire thing, lifted right out of the library. So the data type TT is representing terms in this core type theory. So we've got P, which is taking a name type. A name type is either that this is some bound variable which hasn't yet been resolved to a de Bruijn index. Does anyone here not know what de Bruijn indices are? Okay, great. So de Bruijn indices are a way of representing terms where instead of storing the name as, say, a string or something, you store it as a number which counts the number of binders you need to go out to find the binding site of the variable. So if you have like lambda x, y, x plus y, you would then represent that as lambda, lambda, so one for the x and one for the y. And I said x plus y, so that would be then variable 1 plus variable 0. So the variable 1 is counting sort of 0, 1 to get out to the x, and the variable 0 is counting out just to the y. Does that make sense? Okay, great. De Bruijn index variables are this V constructor here. So typically, variables will be represented using that. Sometimes, though, it's more convenient to use a name, so we can use bound for that. Ref is referring to a global name, sort of like a globally defined function or data type. Or sorry, no, just a globally defined function. Dcon to a data constructor, and tcon to a type constructor. So this ref might be something like plus. This dcon might be cons or nil or 0 or successor, and tcon might be nat or list or monad or whatever. And then there's binders, and then there's various kinds of binders which I didn't list here, but that's things like lambda, pi, let. Then there's applications, constants, and then a few more specialized things like projections, which are runtime projections out of a constructor. So you might say, like, give me the nth field of some constructor. Erased, which is something that's been erased. You don't encounter that very often, but it's convenient to insert it places where you want the compiler to infer something for you. Impossible, and then the type of types, which takes some universe expression, which is important for reasons that aren't at all relevant to this talk, so I'll skip it. Okay. So this term here, SZ. So this is a natural number data type where Z is 0 and S is the successor. So this is the number 1. And it's up in the corner here because I'm going to show you what it looks like reflected. That. Whoa. It's pretty big. So this is using that data type you saw on the last screen. So we have an application of a data constructor with a tag 1 and an arity 1. And it takes the name S in the namespace prelude.nat. And then the type of this binder is a pi binder, so we're binding some irrelevant thing because it just has an arrow type rather than a dependent function type. And that's going to be taking a nat to a nat. And what that's applied to is the sort of 0th constructor, which also happens to have 0 arity here, of prelude.nat, which is called Z, and it's got type nat. And this is really big, and it's really horrible, and it's not fun at all to work with. Yeah.
This is what the internal type theory, I mean, besides the,
Yeah.
it's same representation.
Basically. There's a couple of minor differences, but it's, for all intents and purposes, it's the same thing. So this is what's being generated by that elaboration phase, but then copied up to an Idris data type rather than a Haskell data type. So this, again, you don't want. So an example of what this is like to work with is a data type of proofs that one number is less than another. And we're going to automate construction of that proof. So we have this type less than or equal, which takes two natural numbers and gives back a type. So we have two constructors here. The first one is less than 0, which says that 0 is less than all other numbers m. So like Haskell and unlike Agda, in Idris, if you have an unbound identifier starting with a lowercase number where the system can see what type it must be, then it becomes a universal quantification. So this is saying for all m, 0 is less than or equal to m. And the other way we can show the two numbers are in this relationship is if we can show that n is less than or equal to m, then we know that the successor of n is less than or equal to the successor of n. So a proof then looks like a chain of these less than sucks that's as many deep as the number of sucks on the left of the two numbers, because we go up from 0. And so then we sort of count down to find the difference, is one way to think about this type. Does this type make sense? Or should I explain it again in a different manner? Okay, no hands up. So a couple examples. We can say that less than suck of less than z is of type less than or equal 1, 2. But this isn't actually what's happening. I mean, behind the scenes, the system needs to know what all of these n and m values are. And so if we expand this out, then we see that, in fact, we've got all these implicit arguments. So this syntax with the curly braces means that we're sort of seeing exactly what the implicit argument for something is that otherwise would be hidden to you, because it's typically uninteresting and the system can figure them out on its own. So here we have that in our inner case, we had less than z where m was equal to 1. Right? So if we looking up here, we can see that was a proof that 0 was less than or equal to 1. And because we have a proof that 0 is less than or equal to 1, that is, that n is 0, n is 1 in this constructor, the whole thing is a type less than or equal to 1, 2, because we apply the suck constructor to both of the arguments to get the indices. So let's automate this. So what we want to have is a function that, given two reflected natural numbers, will,
What are we automating on the last slide? Is it the construction of the function that has
So-
the type?
So given two natural numbers, it will attempt to construct a proof that one of them is less than or equal to the other.
By building up those less than or equal
Yeah.
constructors?
Yeah,
So on the previous slide, it was just showing
an example of a proof.
like one, but I guess for like successive terms, it'd be not just like recursively call less than suck on.
So remember that these are constructors. They're not, they're not functions. So I'm using Connor McBride's color scheme here. So red things are data constructors and blue things are type constructors. Green things are functions and purple things are bound variables. So what we're doing here is we're building up a proof term in memory, which is, in this case, a sequence of constructors. And we don't really have a way to sort of split it up or break it down using just the constructors, because that's not what they do. Whereas the idea of this slide is to write a function that, given two reflected representations, will perhaps produce one of those, if it can figure out how to do so. So the idea is that the system is typically unable to infer these kinds of properties. So what we're doing is giving it a procedure to help it do that, which can sort of shift some of the burden away from users of some library and onto the implementer of the library, which is generally a good place for burdens to lie because you can do it once rather than every time you use it. Is that making sense? So you can think of this for the Scala people in the room. If you could change the way that Scala solves an implicit argument or finds an implicit argument in one particular instance, and then say, use these operations instead of these other ones. Which you can kind of do by putting the right things in the right companion objects, but in general, you can't just say, sort of use this procedure I give you here always. Okay. So what we've got here is we have a reflected term and a reflected term, and we're returning perhaps a reflected term. So these ones are the ones that we expect to be the natural numbers that are coming in, and this is the one that's expected to be the less than or equal to type coming out. And we don't know it for sure, remember, because this is all kind of the dirty thing you do in order to make things easy, and then you get the type checker to figure out afterward if you made a mistake. So the first case in the pattern match looks like this. And for the sake of simplicity, I'm starting off with a case where I'm checking if both of them are 0. You could eliminate this and collapse it together with the next case, but it would be somewhat less pedagogical, so I haven't done that here. So here we're checking if we have 0 and if we have 0. And then we're returning less than z with the implicit argument that was that n up there set to 0. So we're applying this constructor to 0. Going onward, if we have a 0 and a suck, then we can apply less than z, and then we set the implicit argument to suck of n, right? So we have this n in here, and then we have this n in here. And yeah, so you can see we have a pattern variable coming down there. This is no fun. The next step is that if we have suck and suck, well then we try checking if we can produce it for the less than cases, right? So we have suck of n and suck of m. And then we get back less than suck, and then we put in the n, the m, and then the proof term that we got back there. I wrote this code. It was really tedious. It was no fun at all. I would not recommend that you do it. It's quite horrible. Finally, we have a case for everything else, which is to say, if we had suck and z, then we wouldn't be able to prove it, but also if somebody put in a list and unit, then we would return nothing. And the idea is that if this returns nothing, there'll be a compile time error, and the system will report something to the user like, I couldn't prove that this number was less than this other number, and I need to know that in order to make this array index look, or this array bounce check statically safe. There's a better way, trust me. So part of why this is ugly is that every single binder has to be completely explicit and type information, because this core type theory is really designed for the type checker to be able to be as simple as possible and as straightforward as possible and as trustworthy as possible. It's not really designed for humans to write it. That's why we have this elaboration procedure. Additionally, all of the implicit arguments, like the n argument to less than z and the n and the m arguments to less than suck, need to be provided explicitly, we saw. The compiler can't infer them like it can when you're working with the real things. And finally, the names need to be written out in full, which is to say, you need to give the full namespace of every name, whereas typically the compiler can look and see you've imported this stuff. Right, so in other words, the compiler does all this. The compiler can infer the types of almost all the binders that you have given a top-level type annotation. The compiler can already solve implicit arguments for you. And the compiler can already use type information to disambiguate names, and it certainly knows what names you have in scope. So why don't we just use the compiler? So Lisp to the rescue. So this is an old school common Lisp macro. I guess there's not any racket people in the room, so I don't have to feel dirty about using unhygienic macros. But so this is a quasi-quotation. And so what this is saying is I'm defining an operator called when, and it's taking some condition and then what this rest keyword means. This is common Lisp, but the similar stuff works in a lot of Lisps. What rest means is take all the rest of the arguments and pack them up in a list called body. So I can give this thing as many arguments as I want. And then what it's going to return is backtick if. So what backtick says is quote this in a way that I can substitute things inside of it. And so then comma means substitute this. That is, instead of taking the quotation, actually evaluate it. So this if symbol is going to be a part of the return syntax from the macro, whereas this comma condition is going to be whatever the value of the variable condition is, which is to say the first argument of this macro. And then the comma at syntax means to unquote, just like comma does, but splice in the contents of the list instead of having them be sort of embedded in the actual list. So this will be a single. So in this case, we put in whatever the contents of the condition variable are, whereas here we take body and we sort of cons prog n on the front. So this is really syntactic sugar for something somewhat more horrible, which gets a lot more horrible when you're writing complicated Lisp macros. So we're taking the list, and then we're taking the quoted symbol if, and then we're not quoting condition, and then we're consing the quoted symbol onto prog-n onto body. So what I want to do, and what I've done, is take this and put it in Idris. So I'm going to use the compiler, and then I can write backtick of parens of suck of z. And that's, once again, evaluating to this horrible mess that we saw earlier. I submit to you that this syntax right here is better than this syntax right here, and I hope you agree with me. Okay, so the extension to the high-level Idris language consists of 3 forms, or 2 depending on how you look at it. There's a quasi-quotation of some term e. There's a quasi-quotation of some term e with some other term t as a goal. So remember that e and t are the same syntactic category here because we have dependent types, so we don't have a separate syntax for types and terms. And then tilde e is the anti-quotation of e, so it's corresponding to the comma. We already used comma for way too many things in Idris, like tuple members and list members and things like that. So I took the meta OCaml or closure syntax instead. What's up?
The type goal,
Yeah.
was that different than you would get if you just said the TE?
So that's, it is here, because if I put that in, then I'm quoting something without evaluating it, so the quoted term would include the.
Okay.
For those who don't know, Idris has an operator called the, which takes a type and a term and returns its second argument, where that term is of the type of the first thing. So it's the identity function where the first argument is the type that it wants for the second argument. And you can use this in order to explicitly give type annotations to things. I saw another hand up.
I was kind of on the same, you
Yeah.
said T is a goal.
Yeah, I'll explain why we want that in a little bit.
What is a goal in Idris? Is that
So so I'm not using it in any sort of technical sense. I like
Okay.
goal in the sense of like, I want this to have this type.
okay?
And that's all.
Okay.
Yeah. So let's take a look at our make TT or make LT function here with quasi-quotation enabled. So one thing to note is that this is working in a pattern. So the syntax for patterns is the same as syntax for other expressions. So I could say quote of z is just of quote of LTZ with the implicit argument m being equal to z. I think this is a better syntax than the one that took up a whole slide. We can also say that make LT of z and suck of anti-quotation of m. So the anti-quotation in a pattern context makes the subterm into a variable that's bound to the reflected syntax that's found there. And the anti-quotation over here is used for building up a term. So it's just like applying a constructor in a pattern or applying a constructor on the right-hand side. In a pattern, it destructures, and in an expression context, it constructs something. This is working exactly the way you expect it. And then we have our suck case, where we make a recursive call and then apply less than suck with n being anti-quote n, m being anti-quote m, and then the proof underneath being this variable prf that I got from my recursive call. And this do notation here is just the maybe monad that you may know from Haskell. Does this make sense to everybody? Are there any questions about what the syntax means or what the expected semantics are? Yeah.
Slight observation. It hadn't occurred to me that in this context, having the anti-quotation was essentially a binding mechanism on the left-hand side. Because you're saying to bind the actual value to the variable in a on the left-hand side.
So the value that's being bound is the quotation of whatever is underneath the quotation of such.
Exactly.
It's not the actual natural number itself. Right. So this term m on the right hand side, which is bound on the left with the pattern variable m, that has type tt rather than type nat.
Yes.
Okay. Yes, that is the case. Right. So, and then of course there's the case here for anything else, nothing. I fail. Okay. So there's a few points about this. One of them is that all the features of quasi-quotation and anti-quotations work in both pattern context and expression context in exactly the way you'd expect. The second is that all the implicit arguments actually need to be solved. So if I try to take the quasi-quotation of the identity function, it'll actually fail. And this is because the identity function has two arguments. It takes the type that it's the identity at, and then it takes the particular value that it should be returning. And because we're running the entire elaborator behind the scenes, which has to solve all the implicit arguments and has to disambiguate everything in order to produce that quoted value, there's not enough information here. So there's sort of two solutions. One is to explicitly tell it what it should be the identity at. So I can sort of I can give it an explicit argument for the implicit argument, or I can give a goal type. So that's what I meant earlier with the goal types. So I can say I want the identity at nat to nat. And that gives the compiler enough information to solve by unification that the first implicit type argument must have been nat, because then it was able to do this. So I don't believe that there's anything you need the goal type for in order that you couldn't do by explicitly giving a bunch of implicit arguments, but it sure makes things nicer when you have a lot of them. And then the goal types are also used for controlling disambiguation. So in Idris we have quite a bit of overloaded syntax. So if I say this list 1012, that could be a list of int, or it can be a vector of some number of natural numbers. And all the ordinary elaboration mechanisms are happening here, which means that the compiler is able to figure out that this is in fact 3, and it's able to figure out that these are nats and all of that stuff. So note that we have a sort of identical syntax for values that really have nothing to do with each other. So that's the other nice use of the goal types. And then if you want to get back something kind of polymorphic, then you can do it by putting explicit anti-quotations where you want the polymorphism. So if I want to be working with the sort of family of identity functions not in any particular type, then I can sort of say lambda x, and then id, where the implicit type argument is whatever that x was. And Idris is smart enough to figure out here that this must have been a TT.
And if say I had a function where it was rather than implicitly polymorphic, I actually explicitly qualified over a set or its type in Idris.
It's called type, but I understand.
Okay.
I speak some Agda.
But if instead I had a identity function that explicitly quantifies the type, I wouldn't have, it would still be fine. There's no monomorphism restriction here.
Right.
Yeah, okay.
Right. It's just that you need to be able to solve all the implicits in order to have something that's meaningful to quote. So.
The type of that bottom lambda would be then type to type theory?
It'd be TT to TT.
TT?
Yeah. So this is taking a quotation of a type. It's not taking an actual type.
Oh.
And we can't really in general write a function from type to its quotation in TT, because you can't pattern match on types. Another sort of interesting aspect here that took me a little bit to figure out what the right solution was, and I'm pretty sure this is the right solution, is that quoted names should be in the global scope rather than any kind of local scope. And specifically, they should be in the global scope in effect immediately prior to the top level definition that they're part of. And the reason for that is that these quotations, we expect them to escape the place where they're defined. And that means that they would need to know what identifiers are in scope at the site that they're going to be actually sort of reified and spliced into. And there's no real way to know that. So if you want to use something from the scope where you're using it, then you have to be explicit and quantify over it here, and then in the site where you're going to use it, apply it directly.
I mean, you can't use some kind of type mechanism to enforce which names are in scope.
I can use some kind of what?
Use a type mechanism to enforce which names are in scope where you'll be splicing it in.
Potentially, that might work. The reflection mechanism right now is a quite faithful copy of the Haskell data type inside of the Idris compiler, which is used for representing this core type theory. And that one doesn't have any mechanism for tracking names on it. So it would divorce it quite a lot from that context. It might be interesting to explore sort of more strongly typed kinds of reflection, where they say, I need a context which has this, and I'm quoting a term of this type, and things like that. But the goal of the reflection mechanism right now is to give you sort of a fun and hacky way out of needing to do things explicitly like that. So
Template Haskell just introduced a typed
yeah,
template Haskell.
definitely. So something like that is definitely worth exploring. It's more complicated in a dependently typed setting, I think, and more fun. So
I'm
it's
still
not what we're doing here.
lost on the anti-quotation on
Okay.
the last slide.
Yeah,
That's useful to go back to. So
that's very important. So I'm glad you're wanting to go back.
what would happen, what would M be if you didn't put the tilde there on the pattern match?
Then it would be a compiler error, and it would say, I don't know what M is.
Okay, because it's supposed to be some tree of syntax terms, essentially.
Yeah, and so what it would do is it would look for names in the global scope that are called M, and if it finds one, then it'll say, and it's a natural number, then it'll just use that, it'll quote it. Probably it won't. It's certainly not the intention of this code that it do so.
Mm-hmm.
So if it does find one, you've made a mistake. But and then the type system won't help you, and your program will just be wrong, unfortunately. But if you but typically you don't have a top level nat called M, and then
No.
it'll say, I don't know what M is.
So the backtick doesn't like make the whole expression reflect into this syntax.
It does.
This AST.
That's exactly what it does. So the M, let's look at this second case here, where we have Z and suck of M, just because it's a little simpler. So what's going on under the hood is precisely this. This is almost entirely the expansion from the compiler of that quotation. So if you see here, the first case is Z, and the second pattern is an application of a constructor of any type, with any tag and any arity named prelude.nat.s to something called n, which I don't know, a pattern variable n. And that pattern variable n is whatever the subterm of that type was, or of that natural number was. And then we can use it over on the right-hand side. It's n here, sorry, down here with the n. And exactly the same thing is happening in this pattern match here. I called it M here, which I guess wasn't the most pedagogical way to do it, but it says, it's saying that this should be the quotation that is app of prelude.nat.suck.
But
Whereas-
don't quote this M.
Right,
capture.
exactly. Don't quote it, use it like a totally ordinary variable, like any other variable.
Okay.
So these are just TT literals, and then that's the way of inserting actual Idris code into that. I mean,
Yeah, so it's a way to request that the compiler expand the high-level convenient Idris code to the low-level, easily machine checkable Idris code, and then quote it to a data type. So it's saying, compiler, please do the stuff you already do whenever I type something at the REPL, but then quote it for me, and then splice it into my code. Right. So, getting back to what the compiler is doing for us, the elaboration procedure is defined largely as kind of embedded tactic language almost inside of Haskell. So there's a monad defined, which is the elaboration monad, and it's essentially a state monad. And the state consists of things like what's a current goal, so what kind of type are we trying to make? Or rather, what kind of type are we trying to make an inhabitant of? And then it has a notion of the current term, which may or may not be a valid inhabitant of that type. If it is, then we can solve it and say, this works. If it isn't, and we try to solve it, then we'll get back to type error. And then there's also a notion of holes, so there can be any number of holes in the current term. And then we go over the holes, solving them one for one. Solving one hole may cause others to be solved by unification, because the state is also keeping track of a collection of unification problems. Yeah, so we have a goal type, we have the current proof term, then we have this collection of holes that remain, and then these unsolved unification problems. So solving a hole will also trigger unification, which may dispatch some other holes. And then what's happening is the elaborator is then going over the high level, so that desugared Idris we saw back on, I think, slide 3. And as it goes, it builds up an action in this elaboration monad. The result of running that action is the low-level core type theory term. And then there's a separate type checker which runs afterwards, which makes sure that the elaborator didn't do anything wrong. And this is a way of keeping sort of the trusted code base fairly small. Okay. So that's sort of a general high-level overview of what's happening. And just a little example of how this kind of works. And this is a high-level hand-wavy explanation. Let's say we want to take the identity of 0. How do we elaborate that? Well, the first thing is the desugaring process is going to notice that ID actually has an extra argument. So we insert a position for that. So we make all of the implicit arguments explicit. So we got A is something. We don't know what. We know it's a type by looking at the type of ID, but that's it. And then you introduce a new hole for every unknown implicit argument. So here we have this question B is what you would call like a hole binding. So it uses the same binding rules as like lambda or whatever. And then we're saying that this B here, well, whatever it is, it's what's going in here. And it may also occur in multiple locations depending on how the term is put together. And then also when we introduce a new hole, then we're adding it to our list of holes that we need to fill out. Then we elaborate the function and its arguments. So we're calling this process recursively. And this is where I wave my hands. And then it's solving holes by unification. So what happens is we elaborate ID, and we get back that it's a function of A colon type to A, and then we get to the second argument and we see that, well, we know it's some kind of type, we don't know what yet, so we say, all right, I'll punt on that for now. Then we get to the 0, and we see that, okay, we know that this is an A. Whatever that first argument to the identity function was, this is the same. And we know that the type of 0 is nat, thus we can infer that that must have been nat. And that's where the unification problem is getting closed out, solves other holes. So now that you've had a little taste of that, that was all stuff that Edwin invented. The quasi-quotation that's being described here, if we want to, let's say we want to elaborate an example of F applied to anti-quota E. That is, quasi-quote F applied to anti-quote E. So the first step is that we replace all the anti-quotations, in this case E, with fresh names. And so the intuition behind this is that in order to sort of figure out what term this is, we need to be able to do so without actually knowing what that term is, because it could be anything. Right? In the case of a pattern, it's going to be whatever that subterm of the quotation was. In the case that we're building something up, it's going to be some other subterm that we stick in there. Regardless, the elaborator has no way of knowing it. And the way we say, I don't know what this is we make a variable. So we're pulling out all of these anti-quotations and remembering which ones correspond to which of those, because later we're going to need them. So now we have f of some variable n. And we're remembering that n was this sub-expression e. Then we elaborate this in a fresh proof state. So in other words, we have all this other proof state with a current term and a goal type and a whole queue and all that stuff. Push it to the side and make a new one. And that's in order to get this global scoping rules that we have for the quasi-quotations. And so then we want to be able to infer all the types for all of these variables. And the way you do that is introduce a hole and say, this hole is of type, and then this thing is of type the hole I just made, and then things will get solved through unification if possible, and if not, will fail. And that's exactly the semantic we want, and that's how most of the inference works inside of the elaborator. So we have, now we have our term is f applied to some n, the type of which hopefully will be inferred through unification. The next step is to quote that result, but because we've remembered what these names are, that is, we remembered what we've called these subterms that have yet to be inserted, then we leave those alone. So rather than having a quote of a reference to something unknown thing called n, we leave the n in place. But now we've got application of the global reference f with some type that's been erased, which is a little trick which gets the compiler to figure out what it must have been later. Then we have n. Finally, all of these n's, we elaborate those back into these holes, which are named by the n. But this time, instead of inferring the type, we give it the type tt, because we know that any subterm of a quoted term will have type tt. And in a pattern context, elaborating something gives you back a pattern variable or a pattern match in general, and elaborating something in an expression context already gives you the right semantics for building that up. So we just piggyback on top of that. And so I've got a draft paper which you can find on the pre-proceedings for IFL if you want to read all of the details of how this elaboration is put together. At the time I wrote it, there was no nested quasi-quotation. That's since been implemented, so take that with a grain of salt until I have a chance to update it. Then also there's more details on the specifics of how the pattern elaboration works, because it's got a couple little tricks in order to make it match things appropriately, mainly with regards to names that the machine invents for things that are irrelevant to users. And then there's some more examples. And thanks for listening to this, and I can show you a couple demonstrations in a little bit if you want. Do you want to drive the demo machine? So for those watching a video who weren't here for the pre-discussion, we had some hookup issues with my laptop. So we're on Life's laptop, and I really don't know how to use Vim very well, so he's going to be showing you things. So here's a couple examples that are written for the paper, which you can read in there, but I figure a little demo is always fun when I have more than a 20-minute conference talk. So this is an example of a little language for putting together rewrite rules for use in proofs. And the specific example that's encoded here is for rewriting additions of natural numbers to a kind of semi-normal form, which automates a lot of hand rewritings of things. So in other words, we're using commutativity and associativity and rules, and the fact that 0 is a right identity to move everything to a form which is convenient to work with. So we've got a couple of functions here, which are serving as the basis. So we have a function called rewrite app. And what rewrite app is doing is it's taking some function which takes a term and then maybe gives back a reflective tactic. And then it will take another term, and if that term is in fact an application, then we'll try, or no, then what it'll do is it'll attempt to apply the rewriting rule and continue doing that, right? So what it'll do is it'll apply the rewrite rule to the term, and if it returned an actual tactic, then it returns the tactic. And if it fails to rewrite that, then it'll rewrite whatever's in the sort of function position, and then whatever's in the argument position. And so this is just the alternative instance on maybe. Right, so it'll try rewriting terms, then functions, then arguments. Then there's also a function called rewrite nat, and what that does is it checks, first it tries to rewrite using whatever rule you've given it. If that fails, then it checks if the term in question is a successor of some other term. So here's a quasi-quote. And if it's indeed that, then it will try to apply the same rewrite rule to the argument. And if it's an addition, then it'll try to rewrite the n and the m. And we can build up lots of functions like this. Kengichi, go a little bit. Oh, question.
Yeah, I'm trying to read this like Haskell, it's not working. So what's being pattern matched here that just tack and nothing?
So that's this term, that's this expression here.
Oh, okay,
so with is giving you something basically like a case.
Okay.
The difference between with and case is that with is on the left-hand side rather than on the right-hand side. And that means you can get dependencies between that and the other things that you're matching on. In this case, I think it looked prettier than a case. And there's no interesting dependencies, which is why there's nothing before this vertical bar.
Okay.
So thanks for asking that. Sometimes I forget the syntactic things that are the same and the syntactic things that are not the same. Okay. And then, so if you could get this, whoa. That's good. Right. So those are a couple, so those are two things that apply rewriting rules sort of recursively based on whether things are applications or based on whether they have certain kinds of structures of nat terms that we see. These rewrite rules are functions that we could then pass to those sort of combinators, right? So their first argument was TT to maybe tactic. These functions are actually TT to maybe tactic. So what this one is doing is if it sees a successor on the right-hand side, then it'll move it outward. So in Idris, the plus function in the library that comes with the compiler, we don't like to call it the standard library because we haven't really sat down and thought through is this actually something that should be standard? But plus is defined recursively on its first argument. And that means that there's no pattern that would catch this case, which means you have to sit down and actually prove that you can move the successor out from the second argument and wrap it around the whole thing. And it's a fairly straightforward proof by induction, and then we have it in the library, but then you have to rewrite with it by hand, and that's no fun. So what this will do is if it sees that the thing you're trying to rewrite looks like plus of some n and then a suck of some m, then it's going to return tactic, which is just rewrite, and then the reflected proof that those things are in fact equal. Sorry for this going off the right-hand side of the screen. Oh, hey, you have word wrapping turned on. Awesome. Yeah, so it's saying plus suck, right suck of n and m, which are these two subterms here. So basically, it looks like something that you would type in the sort of tactic-based prover that comes with Idris. It's just doing it with reflection as automation. And we have the same thing if we have 0 as the second argument to plus, then it won't automatically reduce because plus is recursive on the first argument. So we need to prove that, that this is the case, and we have something called plus 0 right neutral in the library, and then sim here is just symmetry of equality because the equality has to point the right direction, and it doesn't happen to for my purposes here. So this is, once again, a quoted term. Okay, so if I can get you to go a little further. Oh, okay, here's a bit. All right. So the next steps are to then define some sort of general machinery for putting these together into a way that you can use to specify whatever rewrites you want for a particular situation. So there's this sort of alternative combinator, and that's taking two of these functions, tt to maybe tactic, and returning a new function, tt to maybe tactic. And so what it does is we have our two rewrite functions, and then it's a new function which is taking some goal and then attempting to apply the first one and then attempting to apply the second one. So if this one is nothing, then it'll be whatever the result of the second one is. If this one actually returns a result, then it'll be that result. And then there's rewrite eq, which is taking the equality type. So if we have thanks. So if we have an equality where the type arguments are anything and the term arguments are x and y, well then we try rewriting x and then we try rewriting y. And if it's anything else, then we just punt, run for it. And then, am I pushing something on this? I think that my change slide button, which is next to my laser button, is making your screen up. Sorry.
Probably like left mouse.
Yeah, or something. Page up and page down would be my guess. But I'll be careful when I'm pressing the little green button now. Okay. So then we can compose these things to make a rewrite rule for plus, right? So once we've got all these put together, then we're taking, so simplify plus takes a nat as an argument, which is sort of the maximum depth to search, and this is to avoid infinite loops at compile time, like you asked about earlier. And then it's taking a list, so this list of TT name binder TT, that represents a proof context. So when user tactic scripts run, you have the current local scope available, and then you have a goal, which is the type you're trying to inhabit available, and then we're returning a reflected tactic. So in the case with 0, then we use this skip tactic, which means do nothing. And then in the case where we have context and a goal, and we actually have k steps remaining to do work in, then it's taking, this is perhaps a little bit too pointless of style here. So maybe is sort of a straightforwardly typed, a non-dependently typed eliminator for the maybe type. So it's saying what to do in the nothing case, and then what to do in the just case, and then what to do it on. So what we're saying is we try rewrite at, which is that combinator to take a rewrite rule and run it recursively over applications. And then rewrite plus suck right suck or rewrite plus 0 right neutral is the thing that we're putting over all applications. It's not using the equality one because that is actually just an application. It's mainly there to demonstrate things that can work. And then it'll apply that to the goal. So if that fails, then it just does nothing. If it succeeds, then it runs apply tactic, which is a tactic that that takes a term which is one of these tactic functions and then runs it in the tactic environment. So this is sort of a hack to get back recursion where we really need a better tactic language that actually supports it. And then it's quoting an application of simplify plus to anti-quote of quote applied decay. So this function here, quote, there's just a type class called quotable, which has to and from tt things. So in the case of 0, it'll return a quoted 0. In the case of suck, it'll return a quoted suck of its quoted argument. And then there's a test thing here just to show that it actually works. And what I'm wanting to show is that for all n in nat, plus of plus nn3, which is to say n plus n plus 3, is equal to suck of n plus suck of n plus 0. And then if you could scroll down just a little bit further, we can then use this in a tactic proof and say, so intros here just brings this nat into scope. And then apply tactic simplify plus 10. So simplify plus of 10 is saying with a maximum of 10 rewrite steps, use this simplify plus, and then it takes care of it. And then trivial is used to dispatch the goal. So it might be a more fun demo. Can you get this up in the interactive prover?
Yes.
So you'll have to delete the proof script from the file. Like all good demos, this will probably fail.
Is the tactic stuff part of standard Idris, or is that all those constructors and whatnot?
So just delete this here, I guess.
Yeah.
Good one.
Really to just dd dot dot dot. Okay, great, thanks.
So we're going to prove.
Yeah, Blake, I don't
Yeah,
think
we
we're
don't
going to
know.
see that on the video.
Sorry?
The terminal?
Yeah, pretty small.
This is the, I can, let me try to, okay, edit. You zoom in? Yeah. Can you
That looks
click
better.
Okay,
Nice.
cool. So remember to reload the file real quick. Okay. Right, so we have this, so when you're working with Idris interactively, you have these meta variables that come on. And so that test RHS is this question mark test RHS here. So it's a way of leaving behind something to be filled in later. And in this case, we're doing it with tactic script, but there's other ways to do it as well. Like the interactive editing support for both Emacs and Vim gives you commands for doing things like making a new top-level definition that will fill that out. So try doing a :p of test RHS. Got an extra square bracket there. Okay. So now we're in the interactive prover. And so here we can see we have a goal, which is that for all n in nat, this equality holds. So the intro step was used to bring this n up to an assumption. So now we have plus of plus nn3 is equal to suck of plus n, suck plus n0. And then I think it's capital Z, but with no space.
Oh, plus the.
And then, yeah, plus 0 right neutral. That's got tab support now. And then n. And it didn't do anything. So put sim around it. So say rewrite of sim of, you do like SYM $. Yeah. Okay, so now see that this plus n0 has been replaced with n. And so a lot of filling out these kinds of things is just sitting there fiddling with tactics until some of them work, and it's really not very fun. And we can continue and say, thanks. Yeah, so plus 0 right neutral is saying that n plus 0 is equal to n. And this from integer is an artifact of how overloading of int literals works in Idris. Okay. Thank you very much. So sim applied to that just swaps the two sides. And here we're getting it in a reduced form because we've applied something to it, and that causes things to reduce. So one more thing to try is rewrite of plus suck right suck of suck of n. Oh, so n suck of n. Sorry, I was.
Oh, n and then.
Yeah, I said it wrong. Okay. So now what's happened is one of the sucks that was in there, namely that one, has moved outward. So these are the kinds of rewrites that are being automated entirely in that tactic. So let's get out and try the automated version. So if you do :Q, and then up enter. Right, so now we say intro to get our n in scope, and now apply tactic, and what was it called?
I can hit undo on it.
Yeah, that's good.
Well,
Simplified plus.
simplified.
And 10, because it'll finish within 10 steps.
Oh, that's a lot of holes.
Yeah, but so all of these holes here are sort of intermediate things that will be solved automatically. The key thing is that we now have a goal, which is completely trivial, right? So it's so we get holes based on rewrite rules, but they'll be dispatched later. We don't have to worry about them. Soon I will patch it so they're not showing. But the important thing is that now our goal is just that two obviously equal things are equal to each other. And so we can use a tactic called trivial to take care of that obligation. And taking care of that took care of all those holes as well, and we're totally done. I submit to you that this is a more fun way to write your proof. Okay. But proof, yeah, that works. Don't worry about it. Okay. So proof automation is fun, but we can use reflection for more than just proof automation. If you remember, there's another thing we have in Idris which is called error reflection, which is that we can get a reflected copy of an error message and then rewrite it to something more friendly for a user. So if you wouldn't mind opening the other file in your trusty bin, it's the other one that's a .idr in that directory.
Error rewrite?
Yes. Okay. So what this is doing here, there's maybe a little bit of syntax I need to explain. So this just enables the error reflection extension. And then this error handler, this %error handler pragma means that when the compiler encounters an error, it should try rewriting using this function before just sending it onward. So essentially it inserts this Idris function as a sort of an exception handler inside of the compiler, which can change things. And so it's a function from error, which is a reflected version of the internal compiler representation of errors, just like TT is a reflected version of the internal compiler idea of types and terms. And then it's perhaps returning a list of error report parts, where error report parts are text part, which is a string, or term part, which is a term to be rendered using the pretty printer, or a sub report, which is displayed in an indented sub error message. Okay. So in the case that we cannot unify some x with some vect of length n of some type, and a vect of length m of some type, and then some underlying error message, and then some other stuff that you don't need to worry about. So if we see that, then we check whether or not m is sort of alpha equivalent to m, which is what the eq instance for TT gives you. Then we say just the text part of mismatching vector lengths. So vect is a family that's indexed by natural numbers. So it's saying that the first argument is a natural number saying how many elements the vector has. The second is a type saying what the type of the elements are. And if we're getting back a unification error where these are not the same thing, then we know that the lengths didn't match. So then we can return an error message, which instead of saying I can't unify this complicated expression of natural numbers with this complicated expression, it'll say the lengths don't match. This is not actually something you'd want to use in the library because it would leave information that's useful for diagnosing the error behind. It's merely intended as sort of a short demonstration. There's other ones that are much more useful. And then if it's anything else, we just return nothing, which means to return the error message unchanged. And so here we've got a test term, which is called foo, which is a vect of 4 nats, and it's obviously only got 3 elements. So what happens when this is loaded?
So, mismatch.
Yes. So what it's saying is when it's elaborating the tail of the colon of the cons operation on vects, then the length didn't match. So then we got back our message. And the way that this looked before there were quasi-quotes was really absolutely horrible. I mean, these error rewrite functions were just absolutely gigantically huge, and they were really difficult to write. And that's actually what inspired me to write the quasi-quotation in the first place, rather than using it for proof automation, even though that's shown to be more useful. And then there's been a couple of actual users as well, and they seem to be able to use this. So I think it's here to stay for at least a couple of versions. Okay. So those are my 2 quick demonstrations. If you want a copy of the draft paper, you can get it from the IFL page, or I can email it to you. It's also on my webpage. I can also, if you want, you can give me your email address and I can send you an updated version once I've added stuff about nested quotations. But thanks for coming and thanks for your attention. Are there any more questions?
Do you want to talk about like some of the engineering that went into getting this into the compiler?
Yeah, sure.
And maybe.
Actually, I think the fact that it was really easy can be seen as an argument for why your next language should be written with a tactic-driven elaborator.
Really?
It's the kind of thing where you look at it and you think, oh man, that must have been such a pain, but it wasn't. I had to tweak the parser to add the rules, and then I had to write a couple of fairly trivial but tedious functions to traverse terms and extract all of the anti-quoted subterms. I had to tweak the quotation function so that it took an optional argument, which was a list of names to not quote. And then I had to add one case to the elaborator for terms, which is the one corresponding to quasi-quotations, which does what it says there. And that's really all there was. It took a little bit of thought to get patterns right. So can you go back to the slide file I had there?
This one's
Yes. That doesn't look great.
Let me try.
So try saying escape and then rerunning it. Depending on how your exponent is configured, then events may not be able to grab a full screen either.
Okay, so
So you should be able to say F5 and have it. Nope. Okay.
maybe it's because now I'm mirrored and then the engineer displays.
Yeah. Events is kind of a pain.
Well, I can switch out of mirroring mode.
Okay.
Let's see.
Hey, that's great. Do I have keyboard focus?
Let me switch so that display is.
Okay, now it's red. I see it. Okay, so what was I answering?
You're looking at getting the pattern variables out.
Right, thank you very much. Okay, so if we look at the quotation here of suck of Z, there's this name right here. And that name is just something that the machine invented. So we have this MN here, which is meaning names and machine name, which is something that a user never wrote. And we don't want to match whether or not this sort of string and this unique number are actually the same ones there, because they won't be. But it does matter if it occurs down here. So the pattern elaborator figures out a few extra places to put underscores in the pattern based on whether or not there's names that are not used. So any names that sort of exist but actually aren't free in the subterm that they should be, that's their scope, are converted to universal patterns. Oh yeah, and also these type annotations, right? So so we have this type annotation here. So when we're getting it in, when we have an incoming term, it'll, if it originally was well typed, then we don't have to care about what's there. So some of those will also turn into underscore patterns. So that's just another sort of case of thinking about it a while and then writing a sort of long, tedious function to traverse the term and stick those in the right place.
You wrote those in Haskell, or is this in?
It's written in Haskell.
In Haskell.
The entire compiler is written in Haskell.
Yeah.
We're pushing a little bit more Idris sort of reflective capabilities in, but the compiler itself, we don't really have the manpower to rewrite, or the woman power.
Yeah, bootstrap compilers are kind of a pain too sometimes.
Yeah, I mean, I think our efforts are better used on other stuff at the moment,
Yeah.
but self-hosting would be really fun someday,
Yeah.
once we get some more libraries in place.
People are writing parts like parsers and
Yeah. Papers, and there wouldn't be a lot paper-worthy in implementing it in itself, because it would look a lot like the Haskell code. Hey.
A little unrelated, but related to Idris, or what's on the horizon, or what are the things that you're looking to explore?
So I'm gonna have a little bit less time for Idris in the next few months while I've got my internship here. But, so what I'd really like to put together is a reasonable module system. So like at the top of every Idris file, you write module, but that really should be like module, because it's even less expressive than the default Haskell module system. I mean, basically it means like, here's a name for this file, and everything you import, you transitively get everything they imported, and it's something that's basically a placeholder for something better, and I'd like to write something better. The big problem I'd like to solve is that there's kind of a software engineering issue with dependent types, which is that functions implementations escape. So remember you were saying that this plus function was defined recursive on its first argument. If I redefined it to be recursive on its second argument, I would break everything that uses plus. And in the case of plus, I'd have no reason to want to do that rewrite, but in the case of list functions, oftentimes you'll have one that's convenient to use in types that is not tail recursive, but below stack at runtime. Alternatively, you can write a nice tail recursive implementation that is really inconvenient to have in types, but does not blow stack at runtime. We don't want to have to write two versions of all of our functions and sort of keep track of which one is which. And we could have two different functions and then sort of prove that they're computing the same result, and then postulate functional extensionality, and then everything goes to hell. It's a big mess. So I'd like to explore ways of getting enough extensionality into a module system that it can all go through, but without having to replace the entire core type theory with something like observational type theory, which really should do, but there's just not time for. Or
some higher dimensional type theory that allows you to use isomorphisms to.
we're not turning it into hot. We gotta be able to compute with it first.
That's not the only
Okay,
higher dimensional
okay.
type theory.
Okay. Yes. I think that that's less likely to be practical for writing programs, which is what our real interest is. You look like you've got a retort to that, and that's awesome, because if you've got something that's better, then I'd like to know about it. Because this is an area that I just don't know enough about.
Yeah.
I'm not trying to be snarky and say like, oh, I'd love to hear about it either.
I know you're not being smart.
Yeah.
This is getting into.
And I know that you know a lot more about it than I do, so. Cool. And then so I'd really love to have like a module system that isn't terrible. I think something sort of vaguely MixML inspired, but perhaps less complicated, might be nice. But that's me speculating. I mean, my current stage of that is sort of digesting 30 years of module system research, and that's kind of slow going.
And there's so many bad module systems out there. I mean, just about every language it seems like is not solved that. It might have been like, I'm thinking of like deploying .NET code and Java freaking jars, and how this terrible stomping that you can do on yourself, how these languages didn't solve it, like that. I want to know it later on what types I compiled with without just trusting they'll be in the right location, or the .NET way, like they have this cryptographically some type, but that's the only one I can ever use. But that's probably a lot more than you want to solve.
It's what?
That's probably a lot more than you want to solve for.
So Idris doesn't have any separate compilations, so we can dodge that bullet for now.
Okay.
Right now, the compiler is a whole program compiler. So we have separate type checking. We can type check a module and record the sort of explicit core type theory representation. But when you actually want to generate an executable, then it's walking the entire program, starting in main, through all the libraries you use.
Is that generally true of like Coq and Agda and stuff? Is that something you have to be able to approve, or is it?
It's.
I'm just curious. I'm not sure. I've never used Coq enough to know It's a whole program compiler that does libraries.
So the Coq approach is really to have a notion of extraction rather than compiling Coq itself. So what they try to do is, or what they do is they extract the code written in Coq to some other language, which is then compiled,
Okay.
erasing the stuff that can't be represented in that language. So the most mature one goes to OCaml, but you can also extract Scheme or Haskell code, which is intended to have the same semantics as the Coq code. As far as I know, nobody's actually verified this procedure yet, which would be a really cool thing to have, but it seems to work quite well in practice.
Okay.
With some caveats. Like, it's not something I've used a lot, so I want to be a little careful.
Yeah.
So Agda has a couple of backends. The best maintained one generates a giant Haskell file out of your Agda libraries and then sends that off to GHC. The Haskell file is not in a state that GHC is particularly happy with because there's lots of unsafe coerce all over the place. I saw a post on the mailing list that Andreas Abel's got some students who are going to be working on reducing the number of unsafe coerces. But when you see when there is an unsafe coerce, that causes GHC to turn off a lot of optimizations because it needs the types to do it safely. So you tend to not get sort of well-performing code. I mean, this is what we're really pushing with Idris, is to try to have something where you have a realistic compiler for generating code. And we're getting there. I think that's the aspect where we're ahead of the competition, rather than trailing at their heels, yapping like small dogs.
As far as the distinction in like runtime code versus proving things, I notice, say, in Haskell I tend to use combinators and like maybe or something, whereas in Idris I might tend to use pattern matching and recursion and stuff.
Yeah, that's because Idris is strict.
Yeah, so I don't have to worry about, I don't know. It just seems like in the Haskell I'm just concerned about maintainable code versus in the Idris I'm concerned with like proving things, or I don't know.
So I don't actually sit down and write a lot of proofs. I mean, my mode of use of the system is not as a theorem prover, it's as a programming language where type level programming is less painful than in other languages. So certainly combinators are less useful in a language that's strict by default. And a strict by default language has mostly strict libraries, and that means that you don't have that sort of nice compositionality you have from laziness. You get other things instead. So that's sort of the one aspect. As far as writing proofs, I mean, you have to do it sometimes. I try to do it as little as I can. I don't know how to. Yeah. I don't know if that's answering a question or.
Yeah. Well, yeah. I guess like if I did use combinators and then in Idris, like say the REPL, you see it reduced to normal form when you see the combinators getting reduced to the recursion they're implemented in terms of it. I don't know, it's just hard for me to follow sometimes.
So one thing to keep in mind is that the REPL implements the reduction semantics that occur in the type checker, which are not actually what happens at runtime. So when you're type checking something, you need to be able to actually normalize it, which means evaluating underneath lambdas or underneath binders in general. And you don't do that at runtime. You wait for the function to get its argument before you reduce the body. So there is a command which invokes an interpreter which gives you the runtime semantics, which is :x. So that might help with debugging stuff. It's not nearly as well tested as the core evaluator. So I think there are a couple of bugs, and those are my fault, so I'm sorry. But yeah, so that's another aspect of the evaluation that is different from other functional languages, which is that you actually really have sort of two semantics, and for closed terms they should compute the same value. Rather, for closed terms that pass the totality checker, the two semantics should be equivalent, but for open terms or for partial things, they aren't necessarily. So the compile time evaluation is actually lazy.
But like, so it's a difference, I guess. So if I stir head of empty string,
Yeah.
This returns, well, it doesn't reduce,
Right.
I guess. Whereas if I,
At runtime, that'll give you,
a
yeah.
segfault, I guess.
Yeah.
Yeah.
So there's some ways in which this interpreter invoked by :x doesn't agree entirely with the runtime semantics, but it has the runtime evaluation work.
Okay.
Yeah. So stirhead is a partial function which is in the library, and what it does is it takes the first character of a string. Strings are a primitive type, so we can't sort of pattern match other elements. They're not lists of characters like they are in Haskell. So we have these primitives for getting a hold of the first character and the rest of the string. I realize, this is really not the most efficient way to process strings, but it's sort of good enough for now. So in this case, we know that that prim stirhead of this string will be a character in the type character, but it's actually not something we can reduce, so we get back to the neutral term. Try saying stirhead of the string containing the letter A. And so in this case, it actually did reduce, and that's just a matter of how things are at compile time. So in the compile time evaluator, if it doesn't have a pattern match case that matches, it just stops evaluating, which is also what you see in the case of the variables. So try doing lambda s arrow string head of s. So when we do this, we get a function from string to char, but it doesn't know how to reduce this because there's clearly not a pattern match case for when the argument isn't anything yet. So we don't know how to evaluate that any further. So it's the same reason, this is getting stuck for the same reason that this is getting stuck.
But it doesn't look so stuck. I mean, it doesn't look very alarming.
So try doing lambda s of stirhead of, so now actually it's going to need a type annotation now. So do lambda s colon string, and then do stirhead of the string containing A. So here it actually did reduce under the binder, which is not what the runtime semantics would be. And that's just the distinction between, so these two reduction semantics follow the phase distinction between compile time and runtime. People who claim that there's no phase distinction in dependent types are not telling the truth, at least not entirely. And that's the same thing that we were saying earlier with the prim stirhead. That's how it is. If you haven't told it how to reduce it, it won't reduce it.
So why doesn't it give a pattern match error there? I mean,
It would in compiled code. Actually, it would just segfault and give you a completely useless error message if you're using the default backend.
But the REPL is trying to be nicer, or?
Oh, it's because this might be the behavior you're intending. I mean, for type, for type checking, I mean, it actually won't even reduce things that don't pass the totality checker, which is a way of keeping it safe.
Just module main.
Yeah. So. Yeah, so :exec invokes the compiler on the currently loaded module and then executes the resulting code.
Yeah, so you
Yeah. Cordon.
whereas if I had 0 here, it would work fine.
So we don't try to require that all code be total in order to actually be run. We only require that you pass the totality checker in order to be used in a type because that's what makes the type system safe. If you want to, you can say make everything in this module, or this module anyway. You can say require that it pass the totality checker unless I say otherwise, which is the setting I usually run it in. And that sort of helps keep you honest. But some people will want to write a program that isn't obviously total, and they should be able to do that if they want.
So that's what you did there, is turn the total checker,
Well, this
checker on?
not exactly. That's a REPL command that you can just ask, is this total?
Okay.
So it always runs the checker. The setting I was referring to earlier says reject my program if it fails.
There is an issue where
Are you showing all of our bugs in this video?
Okay.
It's okay.
Basically, the thing is, I deleted the intermediate representation. If I basically reload the file, and this time telling it to make sure it's total, it doesn't actually recheck because there's already the cached version, which is not out of date because I haven't changed anything in the file. So if I did change anything in the file and then rerun it, it would complain, or I just deleted that file, so then it rechecked the file and noticed it wasn't total. But you can do that with the command line flag, or there's a little paragraph you can add. Or you can add annotation to specific things, like you can say total, and you can complain that's not total, or I can just say in the file default total.
And there's 3 settings for that. There's total, partial, and covering. So covering means that it checks for exhaustive patterns, but it does not check that you're actually recursing on smaller things than your input was. So it might run forever, but it won't give you that assertion 0 core dump.
Right, just won't print, it might not print anything.
Yeah.
Some of the things talked about, there's like nice step in the REPL for giving you the type of things, or what did I type here, or documentation on those things. Do we even add something that tells you the source of things? What is I think?
No, source location isn't there yet.
Okay.
It's on my to-do list.
Or like the definition of things. Oh, I
Yeah,
guess.
so you can say :printf soon.
Well, it's maybe add would be more interesting.
What's add? You mean
Plus, sorry. Things like that.
So I really love Slime, which is this common Lisp environment for Emacs. So I've been putting a lot of work into trying to make Idris mode for Emacs as much like Slime as possible without sort of completely giving up on all the nice type stuff. So if you're in Emacs, you can like right click on a name and say like show me the definition, and it pops up a buffer with this thing. So a lot of these features are been implemented to support the Emacs mode, but it's written in such a way that any editor that can implement a really basic parser can use them. The same backend is also used by our IRC bot and by tryidris.org, although that's using an older version. And also because, as we all know, the main purpose of any dependently typed functional programming language is not actually writing programs, but rather writing papers. Idris will help you write your papers. If you wouldn't mind going back, say :pprint. LaTeX 60 plus. Then it gives you a nice highlighted version in a LaTeX file. And if you say the same thing but HTML instead of LaTeX, then you get back some nice highlighted code where there's even little tooltips with doc strings for functions. All the code in the slides was highlighted using this feature, because I got really tired of going into those giant terms and doing it by hand. And I always got it wrong, and so.
Now I just want a way to integrate this with the org Babel functionality.
It's on my to-do list.
Okay.
First I want to get the LIDR syntax so that it works with org mode.
Oh, cool.
I just haven't gotten to it yet because I've been busy. Copenhagen has got this unlit thing that they're looking at putting in Agda now. So I'm hoping we can just use the same library as Agda and implement an org backend for that. Because I would love to write in org mode.
Yes.
That would be so awesome. And just use it to dump my LaTeX and.
Yeah, see, that's what's great about it.
Yeah.
It's just combining all the different formats.
Yeah.
That HTML has been thinking, like, I'd like to get on the right-hand side here, syntax sliding on these error messages, like in for HTML. And,
So the groundwork is there, you just need to do a little bit more. I can help you out with that if you want. Are you using the IDE protocol?
no, I need to convert to that. Right now, this
Okay.
is just text, forget about
Yeah,
that.
so if you use the IDE protocol, like the thing that Emacs and tryidris.org and the IRC bot are using,
Yeah.
there's also a sort of a start of an Atom plugin, but if all of those give full highlighting information for error messages.
There's some stuff available in Vim, like, well, I need to turn off the totality. Let's see what
Yeah, in the Emacs mode, you can also do things like right-click on a name and see like everyone who calls that function and explore that tree. I mean, basically, if Slime has it, I'm trying to implement it. So are you showing the interactive stuff? Or?
Sure. If people are interested.
Is this interesting or? Okay. This is kind of fun, like standing here and then telling him what to do. I don't have that experience of power very often. You're going to confuse it. There's lots of things called map already.
I think it's fine.
Okay.
Map of AB and a, wait.
When you're trying to define list map,
Yeah.
you're going to confuse it because the functor instance already has a map. Right, because fmap is called map as it should be. So try calling it like, yeah, lmap or map prime or something.
So given a function of A to B and a list of A and a list of B,
Ooh, it called them f and x's. So he didn't actually type that line that came in there. The compiler generated it.
So I just hit \D and it gives me a definition for that text signature, like a template starter definition. And then you can, X's pattern matching on that. You've got two possible constructors for a list, nil and cons. I'll split those for you.
I tried using auto on the first goal.
So you can ask, given A and given a B in a function, you want a list of B's. You can just ask it to search for something and it does that, which fits the type of the list of B's. And if I do the same thing here, all it says is my goal is a list of B's. I can just, that fits the type signature, but you probably want something, it's not quite the label you want. So I could type that out, I guess. F applied, well, I mean, you can kind of get some clues from the type of the whole there. So if you need a list of B's, and you've got a list of A's, and you've got this function that turns, well, you have a, you can turn this A into a B by applying this function to it. That's one thing you can do. F of A. And then for the rest of it,
F of x, I think.
Oh, F of x, yes. For the rest of it, you can do a list of B's. Well, you've got this top little type signature will do that for you. So you can just call, cons the rest onto.
So it's basically list with more info.
And then you get some more, info in the type system that specifies more of what you want. So here I'll define that, case split the list onto cases. So here auto, and then here the goal is a bit different. Rather than before where the goal is just a list of B's, here the goal is, we have some more information about empty list won't type check here because it needs to be s of n length. So given that we've got a function made B and an A, and we also have a vector of n A's, and we need our goal is a list of those that's one longer. That can kind of tell you, well, maybe if you apply this function to here and then cons that onto this given list, only turn these into B's, that would satisfy the length requirement. And so if I do auto on that, it figures that out. It works.
You might want to do a printf of vect in the REPL. We can see that the empty vect has length 0 and the cons give you back length s of something, and that's how we knew to use the cons constructor, because it needed something of length s of something.
That was what kind of looked like magic.
It can do like fancy stuff. I don't know, is it just lucky? Well, I mean, the case splitting part, it knows which there's the, what is that? Not eliminators, but it knows.
It's not using eliminators.
It knows there's like two possible constructors for that. Well, I mean, if you have more constructors, we can split those up too. But basically you split unavailable constructor for the data type. And in this part, the auto, would you explain that? Like,
So it's taking, so for every type it knows what, for every sort of family it knows what constructors there are for that family. And then it'll try each of them and see if the result type checks, and they do this recursively up to some predetermined depth. I believe for the interactive version it's 10. And you can invoke the same thing to solve implicit arguments in your program, and that'll use, I think, 1,000 by default, and you can also tell it what depth to search at.
so for like the list case, the goal was a list of bees, and it knows how to construct lists as far as it's either nil or cons, and it says, well, I have nil in scope as the first constructor for lists, and that'll fit the type signature, whereas it has to do a little fancy there.
So it's really quite stupid, but it's happily effective for how stupid it is. If anyone's looking to get started on working on the Idris compiler, right now the code that does all this case splitting is it's fairly stringly typed, and it could use a little bit of a somewhat higher level approach. So if you'd like to sort of rewrite that to use actual term constructors rather than doing sort of basically string replace with some hints, then that would be a really fun project. And fairly doable as well. Like you don't need to understand how the whole compiler works or anything, but it's a good introduction where you learn how sort of one corner works. Are you trying to open it up there?
Yeah.
Oh man. Yeah.
And the Idris compiler you can turn on this log level so you can see what it's doing when it's going through this if you turn up those log levels.
So I think we're reaching the end of the scheduled time. And I need to go and lay down a bit.